The number was 2,109 days. Not a theory, not a conjecture buried in a footnote that someone would need specialist training to locate and interpret. A number. Sitting in the open, in the published record, in the brightness logs, in the spectral plates, in the archived submissions of amateur astronomers writing things down on clear nights in backyards across Europe and North America and Australia and Japan. A number that repeated. A cycle that returned on schedule every 2,109 days, roughly 5 years and 9 months. Like something keeping time in the data long before anyone thought to ask what was keeping it. This is a story about what it takes to follow a number to its conclusion. It begins, in the way that the best astronomical stories tend to begin, not with a discovery, but with an absence, with a question that a field organized itself around avoiding, and with the thing that eventually made avoidance impossible. Find Orion on a clear winter night in the northern hemisphere. Start with his belt, 3 stars in a row, tilted slightly, unmistakable once you've seen them once. Then let your eye travel up and to the left. The reddish star there, the one with an unmistakably warm color compared to the blue-white points around it, is Betelgeuse. It marks the right shoulder of the hunter as you look at him from Earth, which is his upper left from your perspective. It is not a difficult star to locate. It is one of the 10 brightest stars in the night sky. On a good night, it is the color of an ember. It is also one of the largest objects in the local part of the galaxy. If you placed Betelgeuse at the center of our solar system, its surface would extend past the orbit of Jupiter. Everything inside the orbit of Jupiter, Mercury, Venus, Earth, Mars, the asteroid belt, would be inside the star. You would be inside the star. The planet on which you are currently resting would be consumed by an outer atmosphere so extended and so diffuse that the word atmosphere begins to feel inadequate. The object is so large that it strains the vocabulary built for ordinary things. And yet, for most of recorded history, Betelgeuse was simply a red star of variable brightness in a familiar constellation. People watched it change, noted its shifts from brighter to dimmer across weeks and months, and wrote down what they saw. The variability was known to ancient observers. Medieval Arab astronomers referred to it by names that reflected its reddish, irregular character. When systematic stellar photometry began in the 19th century, Betelgeuse was among the first stars to have its brightness charted in anything approaching a continuous record. In 1836, John Herschel noted it formally as a variable star. By 1911, when the American Association of Variable Star Observers was founded and began soliciting brightness estimates from amateur astronomers worldwide, Betelgeuse was already one of the prime objects of interest, conspicuous, accessible, and irregular in ways that rewarded sustained watching. The archive that organization built in Cambridge, Massachusetts, over the following century, became the longest continuous observational record of any evolved massive star in existence. Hundreds of thousands of individual brightness estimates, submissions by mail, later by electronic form. Numbers contributed by people who had no expectation of personal credit, who had simply chosen a star and decided to keep watching it, and who added their measurements to a shared pool that eventually constituted, without anyone specifically intending it, a scientific instrument of extraordinary reach and resolution. The record that Archive built described a star with several overlapping rhythms, a dominant cycle of roughly 400 days, now understood as the fundamental pulsation of the star expanding and contracting, its surface rising and falling in a slow, repetitive breath detectable both in its brightness and in the Doppler shifts of its spectral lines. A shorter oscillation near 185 days, attributed to overtone pulsation modes in the stellar envelope. And then, longer and stranger than either of those, a third periodicity. A cycle lasting approximately 2,109 days. Too slow to be a pulsation. Too regular to be random. Too consistent across too many decades to be dismissed as an artifact of any particular instrument or observer. The field named it the long secondary period, and filed it with the category of things that were acknowledged without being followed. The first measurement that placed Betelgeuse at the center of modern stellar physics was made not with photometry, but with geometry. In 1921, Albert Michelson and Francis Pease attached an interferometer to the top of the 100-inch Hooker telescope at Mount Wilson Observatory in the mountains above Pasadena, California. The instrument was a 20-foot steel beam with mirrors at each end that captured incoming starlight from two separated points and recombined it in controlled interference patterns. The geometry of those patterns revealed the angular size of the source. What Michelson and Pease measured, on a specific night in December of that year, was Betelgeuse's angular diameter, 47 milliarcseconds, at a wavelength of 575 nanometers. That number looks small. It is, in the history of stellar astronomy, extraordinary. It was the first time any star other than the Sun had been resolved as a disk rather than treated as a mathematical point. Betelgeuse had a face. It was possible, in principle, not merely to observe it but to map it, to watch it change its face across seasons. And it did change. The convective structures that carry energy from Betelgeuse's interior to its surface are not the tight, uniform granules visible on the surface of our own Sun. They are enormous, individual cells large enough to swallow the entire inner solar system, and they rise and fall on timescales of months to years, producing asymmetries in the stellar disk that ground-based and space-based imaging can detect and track. Bright plumes of hot gas push up through the photosphere. Dark regions where cooled material has sunk back down spread across portions of the disk. The surface of Betelgeuse is, in the most literal observational sense, a turbulent and continuously evolving landscape. This makes it a magnificent laboratory and a genuinely difficult object to model. Every property you try to measure, the rotation rate, the mass loss, the temperature, the chromospheric activity, is wrapped in the noise of that convective turbulence. Separating the large-scale structural behavior of the star from the shorter timescale chaos of its surface requires long baselines and careful analysis, which is exactly why the long secondary period kept appearing in the data and kept being set aside. Everything about Betelgeuse demanded patience, and the long secondary period demanded the most patience of all. Betelgeuse's evolutionary status places it among the most extreme objects in the local neighborhood of the galaxy. It began its life with somewhere between 15 and 19 times the mass of the Sun. Estimates differ depending on which measurements you trust and which models you apply to them. And it burned through its hydrogen fuel in roughly 8 to 10 million years, a blink in astronomical time. The Sun has been fusing hydrogen for 4.5 billion years, and has roughly another 5 billion years before its hydrogen is exhausted. A star the mass of Betelgeuse does in 10 million years what the Sun will take 10 billion years to accomplish. Because the rate of nuclear burning scales steeply with mass, and a more massive star must maintain enormously higher central pressure and temperature to support its own weight against gravitational collapse. When the hydrogen at the core of a star like Betelgeuse is exhausted, the core contracts and heats rapidly while the outer layers expand. The expansion is extreme. The star's radius grows to somewhere between 700 and 1,000 times the radius of the Sun. The precise number depends on the measurement wavelength and the assumptions in the model, and the surface temperature falls. A blue-white main-sequence star becomes a red supergiant, enormous and cool and red, shedding its outer layers at rates that are, by solar standards, prodigious. Mass loss is not a side effect of being a red supergiant. It is one of the defining facts of the evolutionary phase. Betelgeuse is estimated to have shed roughly 100,000th of a solar mass per year across its supergiant lifetime, a number that sounds modest until you consider that it has been shedding material at roughly that rate for tens of thousands of years, and that the evidence of this shedding is visible in the large-scale structure of the space around the star. Infrared observations have revealed concentric shells of ejected material extending hundreds of astronomical units outward from Betelgeuse, the equivalent of multiple times the diameter of the outer solar system, each shell a record of an earlier phase of elevated mass loss, each one marking a moment in the star's past, when something drove material off the surface more vigorously than usual. The mass loss matters enormously for what comes next. Betelgeuse will explode as a Type II supernova. On that point, the field is unanimous. The question is when, and the answer depends on the star's current evolutionary stage, which depends on the mass of the helium core and the composition of the layers above it, which depends on how much total mass the star has retained versus shed, which depends on the mass loss rate across the entire supergent lifetime. The uncertainty in the mass loss rate propagates into uncertainty about timing. Conservative estimates place the supernova within the next 100,000 years. More specific analyses, particularly a 2023 study by Joyce and colleagues that argued Betelgeuse's 400-day pulsation represents the fundamental acoustic mode of the stellar body, pointing toward a radius exceeding 1,000 solar radii and a position in the core carbon-burning phase, suggests the timeline could be far shorter. If that analysis is correct, Betelgeuse may be in the final phase of nuclear burning before the iron core collapses and the shockwave tears the star apart. Carbon burning lasts, at most, a few hundred years. The stages after carbon burning, neon, oxygen, silicon, are measured in years, then months, then weeks. The end, when it comes, will come quickly. When Betelgeuse explodes, it will be visible to the naked eye in daylight. At 650 light-years, it will outshine the full moon. It will cast visible shadows at night. Every major telescope on Earth and in orbit will be pointed at Orion within minutes of the detection alerts. The neutrino burst from the stellar core collapse will arrive at Earth 8 minutes before the light, and neutrino detectors built and maintained specifically for this event, Super Kamiokande in Japan, IceCube at the South Pole, will fire in sequence and broadcast alerts globally within seconds. It will be the closest observed supernova in recorded human history, 19 times nearer than Kepler's supernova of 1604. No one alive today will forget it. All of this was known. All of this was in the models, in the papers, in the textbooks. The astrophysics of Betelgeuse's end was described in richer detail than almost any other object in stellar astronomy, and the models that described it, from the mass loss to the rotation to the pulsation to the evolutionary timeline, were built, without exception, around the assumption that Betelgeuse was a single star. The long secondary period, 2,109 days. In the literature of the 20th century, it appears in table after table of stellar properties, in review articles on red supergent variability, in papers on the AVSO archive, in discussions of Betelgeuse's multiple periodicities. It was present. It was labeled. It was accompanied, in nearly every treatment, by a variant of the same phrase. The origin of the long secondary period remains uncertain. The explanations that were offered and then abandoned across the decades form a list that is, in retrospect, illuminating. Large-scale non-radial oscillation modes, waves in the stellar interior with geometries more complex than the simple radial pulsation of the dominant 400-day cycle. Rotating convective cells of unusual scale. Circumstellar dust shells that orbited the star and periodically obscured portions of the disk from Earth's perspective. Magnetic activity analogous to the 11-year solar cycle but scaled to a supergiant's longer timescales. Each explanation was proposed, modeled to varying levels of sophistication, and then found wanting when compared against all of the available observational constraints. None of them could reproduce both the photometric variations and the radial velocity variations on the same period simultaneously. None of them cleanly predicted the regularity and persistence of the signal across the century of archived data, and yet the alternative was rarely pursued with rigor. A companion star in a 2,109-day orbit would produce exactly the kind of signal present in the data, a periodic modulation in brightness as the companion occasionally transited and eclipsed, a periodic Doppler shift in the radial velocity record as the primary star was gravitationally pulled toward and away from Earth by its orbiting partner, a regular perturbation in the chromospheric activity as the companion moved through the extended outer atmosphere of the supergiant. The companion hypothesis was not absent from the literature. It appeared as a sentence, sometimes as two sentences, at the end of paragraphs devoted to the other explanations. It was acknowledged and then not followed. The field noted it and moved on. In 2006, a paper by Kiss, Zab, and Betting in the monthly notices of the Royal Astronomical Society analyzed the long secondary periods of a large sample of evolved giant and supergent stars and found the period to be a common feature of the population, present in a substantial fraction of objects and, consistently, unexplained by internal mechanisms. The paper noted the binary companion hypothesis and declined to endorse it. This was not carelessness or negligence. It was the ordinary behavior of a field working with the tools it had developed and the framework it had built. The tools were single-star tools. The framework was single-star physics. The question of whether Betelgeuse was a single star was not a question that the existing toolkit was optimized to answer. There is a particular form of institutional blindness that is distinct from ignorance in the simple sense. It is the blindness that develops when a field becomes so sophisticated in answering a specific category of question that it systematically underweights evidence pointing toward a different category. The field studying Betelgeuse was extraordinarily capable at single-star astrophysics. It had built the most detailed model of any evolved massive star in existence. It could debate the precise nuclear burning phase to within centuries and dispute the mass loss rate to within a factor of 2. What it was not configured to do, and what it did not do for most of a century, was ask whether the most fundamental assumption underlying that model, the assumption that the object was alone, was actually true. The assumption had no evidence behind it. It was simply the default, the starting position, the thing you assumed unless there was a specific reason not to. And the long secondary period sitting in the data since the 1930s was a specific reason. It was a specific, quantified, documented reason that appeared in print decade after decade without being taken seriously enough to generate a real test. The thing that changed, beginning in the early 2020s, was a shift in how the question was framed, rather than a sudden arrival of new data. The data had always been there. What changed was who was asking the question and from which direction they were approaching it. Morgan MacLeod works at the Center for Astrophysics at Harvard and Smithsonian in Cambridge, Massachusetts, and his research focus is binary star dynamics, the physics of how two stars orbiting each other interact, exchange angular momentum, transfer mass, and occasionally merge. His engagement with the Betelgeuse companion problem began not through the photometric archive, but through the radial velocity record, which is a different kind of data with a different kind of history. Radial velocity measurements of Betelgeuse, measurements of the Doppler shift in the star's spectral lines that reveal how fast the star's surface is moving toward or away from the observer, go back to the early 1900s. They come from dozens of observatories, using instruments built across multiple generations of spectrographic technology, combined by successive generations of researchers into a dataset that, by the time MacLeod and his collaborators assembled it systematically in the early 2020s, spanned more than a century of continuous stellar monitoring. No other evolved massive star in the sky has a radial velocity record this long and this densely sampled. When MacLeod ran that century of data through the analytical framework he would normally apply to a binary candidate, looking for periodic signals in the velocity variations that were consistent with orbital motion, rather than with pulsation or convection, he found the long secondary period embedded in the radial velocity record with a clarity that did not require statistical creativity to extract. The signal was there. It had been there in the data from 1910. It had been there in data from the 1930s and 1940s. It was in the Mount Wilson Cowd spectrograph plates from the 1960s, glass plates catalogued in what is now the Carnegie Science Archive, plates that recorded information about Betelgeuse's atmospheric motion in sufficient detail to show the contribution of orbital velocity, plates that had been filed and preserved and never, until this analysis, examined with the binary hypothesis as the organizing frame. The signal was coherent across 17 complete orbital cycles, 2000, 109 days per orbit, 17 orbits across a century, the same period in the data from 1910 as in the data from 2020. A signal that is coherent across 17 orbital cycles is not noise. It is not a measurement artifact. It does not arise from the stochastic turbulence of a stellar atmosphere. It is a clock. It is the most reliable periodic signal in the entire Betelgeuse dataset, more regular than the pulsations, more consistent than any of the chromospheric variations, and it had been running continuously, in the public record, for 113 years without anyone following it to its conclusion with the rigor it deserved. MacLeod and his collaborators assembled the radial velocity data alongside a century of visual magnitude measurements and astrometric records, measurements of the star's position in the sky that could reveal a wobble in its proper motion induced by the gravitational pull of an orbiting companion. The three datasets, analyzed together, pointed to the same answer: a companion star, a mass of approximately 0.6 solar masses with an uncertainty of plus or minus 0.14, an orbital period of 2,109 days, plus or minus 9, an orbital separation of approximately 3 times Betelgeuse's own stellar radius, close enough to be orbiting inside the extended outer atmosphere of the supergiant, inside the chromosphere, moving through the hot, turbulent plasma that extends above the visible surface of the star. The paper, published in the Astrophysical Journal in January 2025, was careful in its language. It said the data were consistent with a companion. It calculated the probability that the signal could be produced by something other than a companion in this specific orbit, and found the probability too low to take seriously as an alternative. It made predictions. It said the companion's maximum angular separation from Betelgeuse would occur around December 6, 2024. It said that at maximum separation, the companion would be approximately 52 milliarc seconds from the center of the star, at a position angle of 115 degrees east of north. These were not ranges. They were predictions. Specific, falsifiable, precise enough to test with an observation. If a companion existed in this orbit, it would be at that position on that date. If someone had an instrument capable of resolving 52 milliarc seconds and was pointed at Betelgeuse within the relevant window, the companion would either be there or it would not. Simultaneously and independently, a second group, Jared Goldberg, Meredith Joyce, and Leslie Molnar, publishing in the Astrophysical Journal in late 2024, arrived at the same conclusion through a different route. Goldberg and colleagues evaluated the full list of proposed explanations for the long secondary period and worked through each one against all available observational constraints. Their analysis concluded that a companion star accompanied by a trailing cloud of dust was the only explanation capable of reproducing both the photometric and radial velocity variations simultaneously. Two independent groups, working from different subsets of the same century of data, converging on the same object at the same orbital address. The rotation anomaly, which had troubled single-star models for years, slotted cleanly into this picture. Betelgeuse rotates at approximately 5 kilometers per second at its surface, a number measured from ALMA radio observations in the late 2010s and confirmed by subsequent analyses. For a star that began with 15 to 19 solar masses and has been expanding and losing angular momentum across its supergent phase, this rotation rate is 2 orders of magnitude faster than single-star evolution can account for. Something had spun Betelgeuse up. A companion in a close orbit transfers angular momentum to the primary through tidal interactions, coupling the companion's orbital motion to the primary's rotation and accelerating it over millions of years. The degree of spin-up predicted by the binary model for a companion of this mass in this orbit was consistent with the observed rotation rate. The anomaly was not a separate puzzle. It was the same puzzle, contributing another data point to the same answer that was accumulating across the entire dataset. What changed in late 2024 was not the theory. The theory was already there, in 2 peer-reviewed publications with specific predictions attached. What changed was the existence of a narrow observational window that would not remain open for long. The companion, if it existed, would spend most of its orbit partially or completely hidden behind Betelgeuse as seen from Earth's perspective. The geometry of the orbit meant that the companion would only be at maximum angular separation, the point at which it was farthest from the center of Betelgeuse in the projected skyplane, for a brief window around December 2024. After that, it would move back behind the disk of Betelgeuse and stay there, eclipsed by the star it orbited, unobservable in direct imaging, for approximately the next 2 to 3 years. Miss the window and wait until 2027 for the next comparable opportunity. The prediction had given the companion not just an address, but a deadline. Steve Howell is a senior research scientist at NASA's Ames Research Center in Mountain View, California, and his professional specialty is high-resolution optical imaging from the ground, specifically a technique called speckle imaging, which he had spent years developing and refining in the context of exoplanet host star surveys. The instrument he worked with most closely was called alapike, the Hawaiian word for fox, a speckle imager mounted on the Gemini North telescope on Mauna Kea in Hawaii, operating behind the 8.1-meter mirror that gives Gemini North its light collecting power. Speckle imaging addresses one of the fundamental limitations of ground-based astronomy in a specific and elegant way. When light from a star passes through Earth's atmosphere on its way to a telescope, the turbulence in the air bends and distorts the wavefront continuously, blurring the stellar image and limiting the resolution to something far worse than the telescope's theoretical capability. A conventional long-exposure image of a bright star through the atmosphere is not what the telescope could show you if the air were still. It is what the air permits you to see, which is considerably less. The diffraction limit of Gemini North's 8.1-meter mirror at visible wavelengths corresponds to an angular resolution of approximately 18 milliarc seconds. The atmosphere typically degrades that to something in the range of 500 to 1,000 milliarc seconds, depending on conditions. You are leaving most of the telescope's capability on the table every time you take a conventional long-exposure image. Speckle imaging recovers that lost capability by using the atmosphere's problem as a resource. Instead of one long exposure, it takes thousands of extremely short ones, exposures measured in tens of milliseconds, short enough to freeze the atmospheric turbulence at a single instantaneous state before the air has time to evolve further. Each short exposure is a speckle pattern, a chaotic-looking interference pattern produced by the frozen atmospheric distortion acting on the incoming wavefront, but one that contains, encoded within the chaos, the true image of the stellar source. A mathematical technique called power spectrum analysis combines the thousands of individual exposures, extracts the coherent information from each one while averaging out the incoherent noise, and reconstructs an image at the diffraction limit of the telescope. You get what the telescope is actually capable of showing you, not what the atmosphere is willing to permit. At the predicted separation of 52 milliarc seconds, the companion would be resolvable in principle with alapike on Gemini North. Whether it was resolvable in practice depended on contrast, how much fainter the companion was than Betelgeuse at the wavelengths the instrument was observing. The predicted brightness difference was approximately 6 magnitudes at 466 nanometers, a wavelength in the blue part of the visible spectrum where the temperature difference between the hot companion and the cool red supergent would be most favorable for detection. 6 magnitudes corresponds to a brightness ratio of approximately 250 to 1. The instrument was being asked to detect a faint object separated by less than 3 times the diffraction limit from a source that was 250 times brighter. Several previous attempts to image the companion using space-based telescopes had failed. Published papers had noted that direct detection might be beyond the capability of existing instrumentation. Howell read those papers. He looked at the predicted position, the predicted brightness, the predicted date, and he judged that alapike, used carefully with the best processing, had a reasonable chance of succeeding where space-based instruments had not. The observation was made on December 9, 2024, 3 days after the predicted date of maximum separation, close enough that the positional difference was negligible within the uncertainties. The Gemini North telescope was pointed at Betelgeuse. Alapeak acquired the target. Thousands of short exposures accumulated. The processing pipeline ran. At the predicted position, 52 milliarc seconds from the center of Betelgeuse, at a position angle consistent with 115 degrees east of north, there was something. A faint point source. Blue-white in color, consistent with a stellar object rather than an instrumental artifact. The magnitude difference between the point source and Betelgeuse was approximately 6 magnitudes at 466 nanometers, consistent with the prediction. The implied mass, given the distance to Betelgeuse and reasonable assumptions about the object's temperature and luminosity, was approximately 1.5 solar masses, broadly consistent with the predicted range. The detection significance was 1.5 sigma. In the statistical language of astrophysics, 1.5 sigma means the probability of the signal being a random fluctuation rather than a real source is approximately 13%. The standard threshold for a claimed detection in the field is 5 sigma, a false positive probability of less than 1 in 3.5 million. By that standard, 1.5 sigma is a candidate, not a confirmation. It is something that agrees with the prediction but cannot, on this observation alone, be formally endorsed. Howell announced it anyway, with appropriate hedging, because of what the result actually contained beyond its headline significance number. The object was at the predicted position. The magnitude difference matched the prediction. The color was consistent with the prediction. The implied mass was consistent with the prediction. The probability that a random fluctuation would simultaneously reproduce all 4 of those specifically predicted properties was not 13%. It was orders of magnitude lower than 13%. The coincidence of a noise spike with a 4-parameter prediction in all 4 parameters simultaneously does not happen by accident in astronomy. The individual probability of the signal being noise was 13%. The probability that noise would do precisely what a real companion in this orbit would do was negligible. The paper used the phrase probable detection. The press release was appropriately cautious. The companion had been found with high confidence and confirmed at a statistical level that stopped short of the formal threshold, and the next observational window comparable in quality to the December 2024 window would not open until November 2027. Between those dates, the companion would follow the same arc it had been following for 10 million years, moving back behind the disk of Betelgeuse, eclipsed and invisible. Waiting. In the meantime, other instruments were already in motion, approaching the same question from different directions. At Carnegie Mellon University in Pittsburgh, a weekly journal club meeting in the McWilliams Center for Cosmology and Astrophysics had, by early December 2024, become something more urgent than a casual review of recent papers. The McLeod and Goldberg predictions were circulating. The December window was approaching and then arriving. Anna O'Grady, a postdoctoral researcher in the center, recognized something that the previous observational attempts had missed. There had never been a deep X-ray observation of Betelgeuse made during a period when the companion was at maximum separation from the primary. Every prior attempt to search for the companion's X-ray signature had been made when the companion was positioned near or behind the disk of Betelgeuse, where its signal was completely swamped by the primary's emission. The December window was not just a window for optical speckle imaging. It was a window for X-ray astronomy too, the first time in the observational history of the object when a deep Chandra observation could examine the companion's vicinity without Betelgeuse's disk in the way. O'Grady and her collaborators, including Catalin Breivik, the Falco de Benedetti Career Development Professor in Physics at Carnegie Mellon, and Jared Goldberg from the Flatiron Institute, put together a proposal for director's discretionary time on the Chandra X-ray Observatory. Director's discretionary time is a small allocation reserved by major observatories for time-critical observations that could not have been anticipated in normal proposal cycles, events or opportunities that are scientifically important enough to justify interrupting the scheduled observing program. Getting such time approved, especially on an observatory as oversubscribed as Chandra, requires making a compelling case that the science opportunity is genuinely exceptional and genuinely time-limited. Having two debt proposals accepted for the same event, one for Chandra and one for Hubble, is by any measure unusual. The combination of the MacLeod predictions, the Goldberg analysis, and the narrow December window made the case compelling enough that both proposals were accepted. The Chandra observation targeted the region around Betelgeuse, with the deepest X-ray integration yet attempted for this object. What O'Grady expected to find was a compact remnant. Her analysis framework going into the observation was calibrated for the spectral signatures of a white dwarf or a neutron star, the two types of compact objects that form when stars of moderate mass complete their nuclear burning and collapse. A white dwarf at roughly 1 solar mass would be hot, compact, and X-ray luminous in specific ways that Chandra could detect and characterize. A neutron star would be even more energetic. Both would show accretion signatures if the companion was capturing any of the dense material in Betelgeuse's extended atmosphere. And at an orbital separation of only 2.3 stellar radii, deep inside the chromosphere, even a low accretion rate would produce detectable X-ray emission. The Chandra data returned in October 2025. The emission profile of the companion candidate was not consistent with a white dwarf. It was not consistent with a neutron star. There was no evidence of accretion. The X-ray luminosity was softer and lower energy than any compact remnant would produce, but consistent with a completely different category of object, a young stellar object, a pre-main sequence star, an object still in the process of gravitational contraction, still generating its energy through the conversion of gravitational potential energy into heat rather than through nuclear fusion, still technically in the process of becoming a star rather than already being one in the full nuclear sense. The X-ray emission was the signature of magnetic activity, active regions, flares, the violent reconnection of magnetic field lines in a hot plasma, of the kind produced by young magnetically active stars in the early phases of their evolution. Pre-main sequence stars of low to moderate mass are among the strongest X-ray emitters relative to their bolometric luminosity in the stellar population, precisely because their strong magnetic fields and rapid rotation drive vigorous coronal activity. The profile matched this class of objects with enough specificity that the compact remnant hypothesis could be set aside. O'Grady's description of the result, in the practical language of someone who had been expecting one thing and found another, was that the brightness difference between Betelgeuse and its companion was, in her words, absolutely insane, and that the fact that they could confirm something was there showed how far the science had come. What the data said, beneath the professional hedging, was that the companion was not what anyone had assumed it was, and that the history of the system was therefore different from what the theoretical models had been describing. 10 million years old. Both objects, Betelgeuse and its companion, formed from the same molecular cloud in the same gravitational collapse, roughly 10 million years ago. The same cloud, the same collapse, the same epoch of formation, but two condensations rather than one, each accumulating mass at a rate determined by local conditions in the collapsing gas. Betelgeuse accumulated somewhere between 15 and 19 times the mass of the Sun. The companion accumulated somewhere between half and 1 solar mass. The Chandra data and a companion Hubble analysis from the Flatiron Institute constrained the range but could not pin the value more precisely. That difference in accumulated mass, a factor of roughly 15 to 20 between the two objects, produced an evolutionary divergence so extreme that the two stars born at the same moment in the same cloud could not, in 10 million years, be more different in their current states. Mass is destiny in stellar evolution. A star with 15 solar masses burns through its hydrogen in about 10 million years, which is why Betelgeuse is now a red supergiant in the late stages of its nuclear burning sequence, approaching the iron core that will trigger the final collapse. A star with 1 solar mass takes roughly 10 billion years to exhaust its hydrogen, a timescale 1,000 times longer. The Sun has been fusing hydrogen for 4.5 billion years and is, in stellar evolutionary terms, at approximately the midpoint of its ordinary life. One solar mass is a slow, patient, long-lived configuration. It takes its time. But the companion of Betelgeuse has not even reached the starting point of that long life. With a mass somewhere between half and one solar mass, it has not crossed the threshold at which hydrogen fusion begins. It is still contracting, still converting gravitational potential energy, the energy released as its mass falls inward under its own gravity, into heat and light. Still technically a pre-main sequence object, still sliding down the Hayashi track on the Hertzsprung-Russell diagram toward the zero-age main sequence, the line at which fusion ignites and the long stable phase of hydrogen burning begins. For an object of one solar mass, the journey from the initial collapse of the molecular cloud condensation to the ignition of hydrogen fusion takes approximately 50 million years. The companion, at 10 million years old, is a fifth of the way through that journey. It has another 40 million years of contraction ahead of it before it begins the nuclear burning sequence that defines the main life of a star. This is genuinely strange. There is no simple intuition that prepares you for the fact that two objects can form simultaneously in the same place, one of them already dying and one of them not yet born in the relevant sense. The companion is not a failed star. It is not an object that tried to ignite and could not. It is an object that will ignite, given enough time. A star in the process of becoming. It has a corona. It has a magnetic field. It produces X-rays. It radiates thermal energy generated by its continuing gravitational contraction. In every observational sense, it is already a star. It simply has not yet crossed the specific threshold that astrophysicists use to define stellar adulthood, the moment when the rate of nuclear energy generation precisely balances the rate of energy loss from the surface. The companion is 10 million years old and still approaching that threshold. Betelgeuse is 10 million years old and has already passed through hydrogen burning, helium burning, and carbon burning, and is somewhere in the later phases of its nuclear sequence, building the iron core that cannot burn and cannot support the star's weight against gravity. The two objects exist at opposite ends of the stellar life cycle, frozen in that opposition by nothing more than the accident of how much mass each of them gathered from the same cloud at the same moment. This pairing had no template in the astronomical literature. The field of extreme mass ratio binary research, the study of binary systems where one object is vastly more massive than its companion, had focused primarily on compact remnant systems, where a neutron star or black hole orbits a normal star, or on main sequence systems with ordinary mass ratios. A system consisting of a dying red supergiant and a pre-main sequence companion of low mass, orbiting each other since their formation at a separation of only a few astronomical units, was not a configuration that had been characterized before. O'Grady's paper, in describing the discovery, noted that this opened a new regime of extreme mass ratio binaries. The phrase was restrained. It is the language of careful scientific writing. What it described was a system that had never been seen. The name Siwarha, proposed by Howell's team and subsequently adopted by the International Astronomical Union, comes from Arabic, meaning her bracelet. The name Betelgeuse itself derives from Arabic, roughly, the hand of Al-Jawza, the female figure at the center of the constellation the ancient Arabs saw in the grouping that later became Orion. Her bracelet orbiting her hand. The naming is careful and appropriate. It traces a thread from the same language and the same tradition of careful star watching that gave us the original name, and it places the companion within that tradition rather than outside it. Siwarha, at an orbital separation of approximately 4 astronomical units from the center of Betelgeuse. For reference, 4 astronomical units is roughly the distance between the Sun and Jupiter, is not moving through empty space. It is moving through the extended outer atmosphere of a red supergiant, a region filled with hot, turbulent, partially ionized gas being continuously driven outward by the combination of pulsational shock waves and radiation pressure. The chromosphere of Betelgeuse, as measured from ultraviolet observations, extends to a diameter of at least 270 milliarcseconds, corresponding to roughly 6.4 stellar radii. Siwara's orbit, at 2.3 stellar radii from the center, places it well within this chromospheric region. It is not orbiting near Betelgeuse. It is orbiting inside Betelgeuse's extended atmosphere, moving through the plasma that fills the space above the visible surface. Siwara's orbital velocity, given its distance and the mass of the primary, is approximately 43 kilometers per second. The medium it moves through has a sound speed of roughly 6 kilometers per second at representative chromospheric temperatures. The ratio of Siwara's orbital velocity to the local sound speed, the Mach number of its passage through the chromosphere, is approximately 7. A companion moving at Mach 7 through a dense medium does not pass through it cleanly. It pushes the medium ahead of it, compresses it, heats it in a shock, and drags a wake of denser, disturbed material behind it. The wake is not a metaphor. It is a physical structure, compressed, shocked gas trailing along the companion's orbital path, expanding laterally at the local sound speed as it moves, widening with time as the companion progresses around the orbit. The drag from this medium is cumulative. Each orbit deposits energy into the atmosphere. The orbital energy decreases. The separation decreases. The orbit decays. The current in spiral timescale, based on the estimated density of the chromospheric material and the orbital parameters, is approximately 10,000 years. In 10,000 years, Siwara will have spiraled close enough to the surface of Betelgeuse that tidal forces will begin to exceed its own self-gravity, and the star will begin to be disrupted. Or Betelgeuse will explode as a supernova before the in-spiral completes, and Siwara will be engulfed in the explosion, the shock wave traveling outward at a substantial fraction of the speed of light. The radiation pulse overwhelming a companion that was, in the moment of the explosion, still 10 million years from becoming a star in the nuclear sense. Either way, Siwara does not survive. It was born into an orbit it cannot escape, around a star it cannot outlast. It has been in that orbit for 10 million years, orbiting with the mathematical patience of a body obeying gravity, leaving its signature in the spectrum and the photometry and the radial velocity record, waiting without any capacity for anticipation for an end that was written into the initial conditions of its formation.
The wake was how Hubble confirmed it. Andrea Dupree had been running an ultraviolet spectroscopic campaign on Betelgeuse from the Center for Astrophysics at Harvard and Smithsonian for nearly a decade. 8 years of observations with the Hubble Space Telescope imaging spectrograph, using a tiny aperture 0.025 by 0.1 arcseconds, targeted at the center of Betelgeuse's disk, capturing the ultraviolet spectrum of the star's chromosphere across the full span of wavelengths accessible to the instrument from around 2300 to 3000 angstroms.
The specific lines she was watching were chosen because they are diagnostic of atmospheric dynamics rather than just atmospheric temperature. Chromospheric emission lines of singly ionized iron, Fe2 at 2382, 2585, 2692, 2724, 2727, and 2730 angstroms, along with neutral silicon at 2516 angstroms, and neutral magnesium at 2852 angstroms. These are strong transitions from low-lying energy levels, sensitive to mass motions in the chromosphere, through the asymmetries they develop in their emission profiles when gas is moving systematically toward or away from the observer. A line profile that is symmetric means the chromospheric gas is not moving coherently. A line profile that is asymmetric with the blue emission peak stronger or weaker than the red emission peak means gas is flowing outward or inward through the region where those photons are being produced. Dupree also tracked optical spectra from ground-based observatories, from the Hermes spectrograph on the 1.2-meter Mercator telescope at La Palma in the Canary Islands, and from TRES, the high-throughput Echelle spectrograph, on the 1.5-meter Tillinghast telescope at the Fred Lawrence Whipple Observatory at Mount Hopkins in Arizona. The optical spectra covered the region around 4030 angstroms, where 3 transitions of neutral manganese, M and I, at 4030, 75, 4033 but 07, and 4034 49 angstroms, produced narrow absorption features against the broader photospheric background. These manganese lines arise from the ground level of neutral manganese atoms in the circumstellar material surrounding Betelgeuse, material that is not part of the star's photosphere or chromosphere proper, but exists in the extended envelope at larger distances. absorbing background starlight as it passes through. When she assembled 8 years of these observations, covering more than one full orbital cycle of the companion, from 2017 through 2025, and folded them against the orbital period established by MacLeod's analysis, the pattern that emerged was not ambiguous. The circumstellar manganese absorption increased after the companion transited across the face of Betelgeuse and decreased in the period leading up to the next transit. The increase reached its maximum near the orbital phase corresponding to eclipse, when the companion passed behind the star as seen from Earth, and then declined steadily toward the following transit. The 3 manganese transitions showed the same pattern, independently, which ruled out instrumental artifacts. The expansion velocity of the circumstellar material, measured from the Doppler shift of the manganese absorption relative to the photospheric line, also varied systematically with orbital phase, approximately -5 kilometers per second at transit, increasing to -10 to -15 kilometers per second at eclipse, then decreasing back toward the next transit. The chromosphere was being pushed outward, and the pushing varied on the same 2109-day clock. The ultraviolet iron emission lines from Hubble told the same story. The ratio of the blue emission peak to the red emission peak in the Fe2 lines decreased after transit and reached a minimum near eclipse, indicating increasing chromospheric outflow during that orbital phase. The silicon and magnesium lines showed the same pattern: 7 independent ultraviolet transitions, 3 independent optical transitions, all of them varying coherently on the orbital period of the companion, all of them pointing in the same physical direction. Something was moving through the atmosphere of Betelgeuse on a regular schedule, pushing gas outward, compressing it into a trailing wake, and the chemical signatures of that wake were written into the spectrum of the star itself. Dupree presented these results at a press conference on January 10, 2026, at the 247th meeting of the American Astronomical Society in Phoenix, Arizona. The paper was accepted for publication in the Astrophysical Journal. The press conference was attended by science journalists from major outlets and streamed online. She described the boat through water analogy, the companion creating a ripple in Betelgeuse's atmosphere that was detectable in the spectral data. She described the 8 years of Hubble time that had gone into the campaign. She said, using words that the press release captured and that reached millions of people across the following days, that for the first time they had direct evidence that a companion was disrupting the atmosphere of the supergent and shaping its appearance and behavior. It was true. It was also a compressed version of a story that was far longer and far stranger than any headline could contain. The great dimming of 2019 and 2020 sits in this story like a door that opens from 2 directions. From one direction, it is a solved problem. Between October 2019 and February 2020, Betelgeuse faded dramatically, dropping from its typical apparent magnitude of around 0.5 to approximately 1.7, a 3-fold decrease in brightness that was measurable in the AVSO archive in real time and visible to the naked eye by anyone who looked at Orion during that winter. The public noticed. The word supernova appeared in headlines. The question being asked on astronomy forums and in science sections of newspapers was whether the dimming was the precursor to the event that astronomers had been anticipating for decades, the final collapse of a star that had been signaling its approach to death for millions of years. The professionals were more cautious. Dupree, who had Hubble time allocated before the dimming began and used it as the dimming was happening, identified a chromospheric brightening in the ultraviolet data that preceded the optical dimming by several months. The sequence of brightening before optical dimming pointed not toward interior collapse but toward an ejection event. A large convective cell had driven a mass ejection from the photosphere, releasing material equivalent to roughly 400 billion times the mass of a typical solar coronal mass ejection. That material, moving outward through the atmosphere, cooled as it expanded and condensed into dust. The dust cloud, spreading across a portion of Betelgeuse's visible disk, blocked enough of the outgoing light to produce the dramatic dimming observed from Earth. The star had not been dying. It had been sneezing, violently, in a way it had almost certainly done many times in its 10-million-year history, but had not done during the century of careful modern observation. This explanation, the surface mass ejection explanation, is correct. The dust was real. The ejection was real. The convective driving mechanism was real. None of that changed when the companion was confirmed. But from the second direction, a question that the solved explanation does not fully answer. What triggered the ejection? MacLeod's paper, in early 2025, noted carefully that if a burst of material ejected from Betelgeuse's surface collided with the existing wake trailing behind the companion, the collision would generate a shock. Shock-heated gas that subsequently cools can, under the right temperature and density conditions, condense into dust with a rapidity that would not occur in the absence of the shock. The speed with which the Great Dimming's dust formed, the abruptness of the optical fading, which had puzzled researchers even after the ejection mechanism was established, was more naturally explained by shock-triggered condensation than by the gradual cooling of freely expanding ejecta. The geometry had to be favorable. The ejection had to occur when the companion was positioned in its orbit such that the ejecta would encounter the wake, rather than miss it entirely. The orbital mechanics, when checked, were consistent with the geometry being favorable in late 2019. Neither the MacLeod paper nor the Dupree paper claimed this was definitively what happened during the Great Dimming. Both noted the consistency and declined to push the claim beyond what the data established. What the notes implied, stated plainly, was that the Great Dimming explanation, already correct at the level at which it was established, might be incomplete at a deeper level. The companion may have contributed to the event that triggered the dimming through a mechanism that was invisible in the analysis because the companion itself was not part of the model in which the analysis was conducted. This matters beyond the specific event of 2019 and 2020. If the companion has been perturbing Betelgeuse's atmosphere continuously for 10 million years, enhancing mass loss in certain orbital phases, triggering dust formation through wake interactions, depositing angular momentum into the chromosphere, shaping the structure of the extended circumstellar shells that extend hundreds of astronomical units from the star, then every estimate of the mass loss rate derived from a single star model is slightly wrong in a systematic direction. And systematic errors in the mass loss rate propagate into errors in the total mass retained, which propagates into errors in the evolutionary stage, which propagates into errors in the supernova timeline. The supernova timeline for a star of Betelgeuse's mass can change by thousands of years depending on the mass loss rate assumed. A slightly elevated mass loss rate, sustained over 10 million years, produces a star with meaningfully less mass at the current epoch, which alters the position in the nuclear burning sequence, which alters when the iron core forms and the collapse is triggered. The error does not have to be large to matter for the timeline. It has to be systematic, and a companion that has been continuously present since the formation of the system is the definition of a systematic effect. The single star model of Betelgeuse was not wrong in the way that wrong models usually fail, not through a bad observational technique or a flawed physical assumption about nuclear burning or convection. It was wrong in the way that models fail when they are built around a question that was never fully asked. Nobody tested whether Betelgeuse was alone because aloneness was not a hypothesis waiting to be confirmed. It was the default. And the long secondary period, the number 2,109 days, present in the record since the 1930s, was the argument that the default was wrong, running in the data for a century, indifferent to whether anyone was following it. The archive of the American Association of Variable Star Observers in Cambridge, Massachusetts, was still receiving brightness estimates on the night of January 10, 2026, while Dupree was presenting at the American Astronomical Society meeting in Phoenix. On that night, for observers in the Northern Hemisphere, Orion was visible in the eastern sky by mid-evening. Betelgeuse was where it always is, upper left of the constellation, reddish, shifting in brightness on cycles that the people looking at it had been tracking for over a century without knowing, most of them, what was underneath the shifts. Some of those observers pointing their telescopes at the star that night and writing down the brightness value they estimated against nearby comparison stars, would later read about the press conference the following morning. Others would not encounter the news at all. The observations would be submitted to the archive regardless, added to a database that had been accumulating without interruption since 1911, building the record that had contained the answer for decades before the question was asked precisely enough to find it. The companion, Siwarha, was behind Betelgeuse on that night. It had moved, following its orbital path to the portion of the orbit where it is eclipsed by the primary from Earth's perspective, where it is invisible and will remain invisible until approximately August 2027. It was following the same arc it had been following for 10 million years, and the fact that astronomers had just confirmed its existence after a century of seeing its effects in the data did not affect its trajectory by a single kilometer. It was there, moving through the dense chromospheric plasma at 43 kilometers per second, generating the wake that Hubble had just documented in iron and silicon and magnesium and manganese, spiraling very slowly inward on a timescale measured in thousands of years, orbiting a star that had been dying since before the companion had begun to live. The next observational window will open in late 2027. Steve Howell and his team have indicated they intend to observe when the window opens, using Alipiki on Gemini North, now with the knowledge of exactly what they are looking for and exactly where to look. The Hubble ultraviolet campaign is continuing. The ground-based spectroscopic monitoring from Hermes and TRES is presumably ongoing, accumulating more of the manganese absorption record that will eventually span multiple orbital cycles and provide a cleaner baseline for understanding the wake's behavior. The Chandra data from October 2025 awaits deeper analysis as the companion's nature is further characterized. What will be different about the November 2027 observation is not the instrument or the target. What will be different is the question being asked of the data. In December 2024, the question was whether the companion existed. In November 2027, the question will be whether the models derived from its confirmation are correct, whether the orbital parameters are precisely what the predictions said, whether the companion's properties can be more tightly constrained with a higher significance detection, whether the wake's spectral signature in the next transit behaves exactly as the current models predict. Each answer generates the question the next observation is designed to answer. What gets confirmed at a press conference in Phoenix in January 2026 is not a discovery in the strict sense of that word. A discovery is the first encounter with something previously unknown. What happened in Phoenix was a ratification, the moment at which the accumulated weight of independent evidence crossed the threshold of collective professional acceptance. Those are different events. The distinction matters. The companion was in the radial velocity data from 1910. It was in the spectral plates from Mount Wilson in 1961. It was in the AVSO brightness archive that hundreds of amateur astronomers had been building since before the Second World War. It was in every period analysis that mentioned the long secondary period and then offered an unsatisfying single-star explanation. It was in the sentence that kept appearing at the end of paragraphs, "The possibility of a binary companion cannot be excluded," and then disappearing before the possibility became a pursuit. It was there for a century, in the public record, not hiding, not obscured by insufficient technology, simply waiting for the question to be asked of it, with sufficient rigor. The MacLeod paper asked that question in 2025. The Goldberg paper asked it in 2024. The Howell observation attempted to answer it in December 2024. The O'Grady-Chandra campaign characterized the answer in October 2025. The Dupree-Hubble campaign documented the answer in chemical detail across 8 years of ultraviolet spectroscopy. The press conference in January 2026 told the public that all of those separate lines of evidence had converged on the same object, and the field was ready to say so out loud. The history of the discovery that appears in most accounts of the story, Hubble confirms hidden companion star, January 2026, is accurate about the endpoint and silent about everything before it. The announcement was the ending. The story was the century before it. There is something worth sitting with at the end of this, Something about what it means that the answer was in the archive all along, accumulating night by night from the observations of people who were simply watching a star and writing down numbers. The AVSO observers, who contributed to the Betelgeuse record across the 20th century, were not searching for a companion. They were not testing the binary hypothesis. They were doing what they had agreed to do, watching a variable star and reporting the brightness to a shared pool. And the record they were building was, without their knowledge, the evidentiary foundation for a discovery that would not be formally announced until most of them were no longer living. The clock did not care whether anyone was reading it. It ran in the data from before the Second World War. It ran through the spectral plates filed away in Carnegie observatories across the middle decades of the century. It ran through every set of AVSO observations submitted by backyard observers on clear nights in hemispheres across the world. It ran through the Hubble ultraviolet spectra accumulated by a researcher who kept applying for observing time because the pattern in the data was too specific to be anything other than what it turned out to be. It ran through the radial velocity record that MacLeod assembled from a century of multi-observatory, multi-generational, multi-instrument measurements, 113 years of data about one star, the longest continuous record of its kind for any evolved massive star in existence. 2,109 days. The time it takes something not yet born to orbit something already dying. Once. The time it took a field to ask the right question of a number it had always known. Siwarha is behind Betelgeuse right now as you listen to this. It is where it always is when it cannot be seen, following the same arc that has defined every moment of its 10 million year existence, moving through the chromospheric plasma at orbital velocity, trailing the wake of compressed gas that Hubble spent 8 years learning to read. The AVSO archive in Cambridge is still open. The brightness estimates are still arriving.
Orion is still visible from the northern hemisphere on clear winter nights, still carrying the red star at his shoulder, still ordinary looking from the ground, variable, slightly shifting in brightness across weeks and months, the changes mixing the 400-day pulsation and the shorter oscillations, and the long 6-year rhythm that is now understood to be the orbital signature of a companion that has been there since the beginning, since the molecular cloud that became both objects collapsed and sorted its mass into 2 unequal portions, since a bracelet began orbiting a hand in a system that has no analog in the existing literature and that no one thought to look for because no one knew to.
The star that generations of astronomers studied as an isolated object was never isolated. It was described as alone because aloneness was assumed, not tested. The model was not built on evidence of isolation. It was built on the absence of evidence for a companion, which is not the same thing, a fact that seems obvious in retrospect and requires a century of overlooked data to make properly vivid. What changes now in the literature will not be dramatic. No paper will be retracted. No conclusion will be formally reversed. The revision of Betelgeuse's single-star models, the mass loss estimates, the rotational history, the evolutionary timeline will happen in the next generation of papers, the ones that take the binary nature of the system as a starting assumption and rebuild from there. They will not announce themselves as corrections. They will simply incorporate Siwarha as a parameter and proceed. The revision will be quiet and thorough. And on the night Betelgeuse finally explodes, whenever that night is, the neutrino burst will arrive first, 8 minutes before the light, and every detector on the planet will fire, and every alert will go out, and every telescope will turn. The data that comes back from those observations will contain, somewhere within it, the record of what happened to Siwarha, whether it was still orbiting when the shockwave arrived, whether the tidal disruption preceded the explosion, whether a star that had been in the process of becoming for 10 million years had enough time to finish the journey, or whether it ended unfinished, still falling inward toward the nuclear threshold it never crossed. The bracelet dissolved in the hand's last light. The number will be in that data too. 2,109 days. The orbital period, the long secondary period, the rhythm that persisted through the spectral plates and the brightness logs and the ultraviolet spectra and the radial velocity records. It will be in the final data the way it was in all the earlier data, not as a mystery any longer, but as a measurement, a known quantity. A fact about a system that turned out to be two things instead of one, and that we spent a century looking at before we were ready to see what was actually there. The number was always the answer. It was waiting for the right question. The archive is still open. The estimates are still arriving. On clear nights, in backyards on several continents, people are still looking at the red shoulder of Orion and writing things down.